Hello, welcome to Atomic Structure and Periodicity Trends, Part 2. So the next trend we're going to get into is electron affinity, which is the energy that is released when a neutral atom gains an electron. We are looking at the change in energy. So take a neutral atom by itself and the amount of energy with it, give it an electron, and then measure its energy after it has gained that electron. The difference between those two states represents the electron affinity. So it's kind of like a state function that we saw with thermodynamics. Not literally a state function, but kind of similar to it in that sense. Just like ionization energy, electron affinity occurs in the gaseous state. From a generic reaction perspective, our reaction would look like this, which kind of the opposite, if you will, of ionization energy. Electron affinity is defined as an exothermic process. However, there may be some that are actually endothermic, kind of, I guess, exceptions to the rule, if you will, since when you gain electrons, you tend to be, as a nonmetal, you tend to be going towards becoming more stable or having a full outer shell like the noble gases. So some of our little exceptions, if you will, the alkaline earth metals, column 2, and all of our noble gases show an endothermic process when gaining an electron. Why is that the case? Well, we got to think about where is that electron going to be put? What orbital? What energy level? What is going on? So I'll let you guys kind of marinate on that one as we move forward. So the energy that is released, the more energy released, the larger the electron affinity is going to be. So we're looking at magnitude in that sense. The more negative the number, the larger the electron affinity, or EA is, shorthand, if you will. Questions on this beginning of electron affinity? Okay? So our trends in electron affinity are kind of all over the place. The alkaline metals decrease in electron affinity down a column. But not all of our groups do this same thing. Looking specifically at the alkali metals, we know that the radius is getting larger. We know that the Z effective is staying basically the same. We know that shielding is also playing a role based on the attraction that the nucleus is going to have for any electron, including here a new electron, being added to an element. Generally, we have irregular increase in the electron affinity from the second period to the third period. So again, going down a column 2, period 2 to period 3, it's irregular. The affinity doesn't really follow a set trend, so to speak, that we've seen in the past. Generally, we increase going across a period. Well, size of radius versus strength of nucleus. You go left to right, the radius gets smaller, the nucleus gets larger, there's going to be a greater attraction. The greater an attraction to the electron, the greater the amount of energy that is released in the process. We become more negative left to right. But again, it's not absolute, since you can see generally is in quotation marks, so it's a general trend, it's not an absolute trend. Nothing seems to be absolute in the world of chemistry these days, or ever, so we just kind of go with it. Group 5A, generally lower electron affinity than expected, because we have that extra electron pair type of repulsion. Think about 5A, that's the nitrogen column. You have one electron in each of the p orbitals, to add the next electron, there's going to be repulsion there. So it's going to lower the amount of energy because the attraction is going to be diminished because of that creating or the creation of an electron pair. Back from the last slide regarding our alkaline earth metals, and the noble gases generally are lower because of where you're adding the next electron to. If I add an electron to an alkaline earth metal, I'm going to the 2p orbital. Or 3p or 4p. If I'm adding an electron to a noble gas, I'm adding to the next higher energy level. Well, noble gases don't want to gain any electrons anyway, but it's going to be the next energy level. It's going to be that much further away. Is getting towards being, again, or is going to be an endothermic process. You're forcing it to happen. So keep in mind, when you're adding an electron to any neutral atom, where is that electron going? What energy level? What orbital? What's going on with the nucleus? There are a lot of things to take into account when trying to compare two things or ranking something based on electron affinity. We do know the highest electron affinity in any period is the halogens. Halogens are 7 valence electrons. They want one more electron really bad to become an ion and to have a full octet in their valence shell. So the most energy will be released when the halogens get that electron. Questions on the trends? Okay. So here's a table. Don't memorize numbers. You're never going to be given numbers. You're always going to base it off the idea of the trend and what's going on. We can kind of see on the noble gases. Here we are. They're all going to be positive. You have to force it to happen. We go over to column 2A. Again, a little bit. Here's beryllium, magnesium are endothermic. As we get bigger and bigger, they start to be exothermic again. Column 5, nitrogen. Nitrogen is endothermic according to the chart. But then we are exothermic as you go down the group. So little hiccups here and there, things to think about. Graphically, on the type of graph we've seen before with atomic radius and ionization energy, everything's been connected. Everything kind of smooth-ish, except for our exceptions. With this one, it's irregular. It's sporadic. Nothing's connected. Nothing kind of really makes sense. And that's unfortunate, but that's just the way it is with electron affinity. Questions on electron affinity? Okay. All right, our last trend, electronegativity. We all are familiar with this one. But again, it deals with the attraction of electrons within a bond. Keep in mind, electron affinity is an atom by itself gaining an electron. Here we have electronegativity also attracting electrons, but within a bond between two atoms. So kind of big, significant difference. From the trend, nothing new here. Increases left to right. It decreases going down a group. Size of radius versus strength of nucleus. Fluorine's the most, francium's the least. Noble gases do not get a value. They don't attract electrons because they don't really form any bonds. Some of the bigger ones, xenon does form compounds and certain things, but again, we're not really worried about it attracting electrons. But keep in mind, electronegativity is the opposite of the atomic radius. Like ionization energy is the opposite of the atomic radius. But it comes down to the larger the difference in electronegativity, the more polar the bond. So this trend does help us figure out bonding characteristics. The negative end of the polar bond is always towards the more electronegative atom. So going back to the larger difference, you're not going to be given any numbers. You have to base this off of the fact of where they're located on the periodic table. Graphically or chart-wise, here's numbers. You'll never be given numbers, but we can kind of see fluorine up there at 4.0, top right. Francium way over on the bottom left, 0.7. But within those non-metals, they're all a little bit different. And the farther apart two atoms are from each other, the more polar the bond, assuming they are both non-metals. The minute you get to metal and the non-metal, obviously got to be ionic. So going along electronegativity and bond type, the numbers you see here, do not worry about them. I have 17 textbooks that have 17 different ranges. From a pure covalent, where it's a difference of 0, you are looking at your diatomic elements. Everything else, non-polar covalent, having a very small difference. They are close to one another on the periodic table, and as you get further and further apart, you become polar until eventually you're a metal and a non-metal, very, very far apart. You are then ionic. There is no more sharing. All you have is a transfer of electrons. Questions on electronegativity? Okay? So to summarize everything, kind of puts everything we've talked about on one little chart. It's not in the locker. School loop no longer exists. But it is in the reference sheets, I believe. So it's a good one to have and keep track of. All right. Summary of bond polarity. All kind of saw this already. Again, the numbers. The difference in electronegativity. Don't worry about those numbers. It ultimately comes down to the placement on the periodic table. And you keep a reference of fluorine as the most. You can figure out polar versus non-polar. All right, dipole moments. A dipole moment is the vector that measures bond polarity, signified by mu, lovely Greek letter, I believe, which, again, just as long as you see the term dipole moment, it's just talking about a polar bond. A dipole is an arrow that you would draw on a dot structure. It has a positive N, it has a negative N. The positive N is literally making a plus sign within your arrow on the opposite end of the point part of the arrow, and the negative end is the point part of the arrow. These dipole moments are directly proportional to the size of the charges and the distance between them. So the size of the arrow is your vector, physics people, that tell you how much polar, that's probably the wrong way of saying it, but how polar something is, smaller arrow compared to larger arrow, and then with the direction that it's going. The equation down here, mu equals Q times R. Q is not heat, R is radius. Coulomb's law, we're going to see a lot more next chapter with bonding. And then it's just the unit of it. Again, you will not have to do anything with dipole moments except figure out, is something polar, and or what direction is the polarity pointing in. But generally, the more electrons two atoms share and the larger the atoms are, the larger the dipole moment is going to be. So from a single to a double to a triple bond, that's more electrons being shared. From 2 to 4 to 6 electrons. Then you get to the size of the atom, does play a role with that size of nucleus as well. More attraction, more electrons, more polar it's going to be. Questions about dipole moments? Okay. Pictorial diagrams, you get an idea of, pure or non-polar versus polar versus ionic. These little symbols represent a partial negative and a partial positive. I don't remember what the Greek symbol is, but yay. And then ionic is just transfer of electrons. You have a full negative. You have a full positive. Polar bond, it's partial, not full. All right, magnetic properties of our lovely transition metals. This is one of those things where in order to really do this and really understand it, you have to have a good grasp of molecular orbital theory. Molecular orbital theory no longer is part of the course. So here we are answering questions about a concept that requires knowledge about a concept that you don't need to know. Yes, welcome to College Board, a bunch of monkeys throwing darts at questions. But anyway, so this whole idea of magnetism comes down to, do you have any unpaired electrons? The easiest way to determine this from an individual atom or ion perspective, draw the orbital diagram. You know, the boxes with the arrows. If you have at least one unpaired electron, you have to be paramagnetic. Therefore, you'll be attracted to a magnetic field. The more electrons that are unpaired in their orbital, the greater the attraction to a magnetic field. Questions on this one? Okay. Conversely, if all of the electrons in all of the orbitals of the atom or ion you are looking at are all paired up, then you are diamagnetic. You are repelled by a magnetic field. You are not attracted to a magnetic field. From a molecule perspective, you have to understand molecular orbital theory, which again is beyond the scope of the course. In the notes on my website, there is a set of notes dealing with molecular orbital theory. There is no video on it, but if you're interested, go check it out, and we can talk about it if you so choose. Any questions on diamagnetism? All right. Thank you very much. Bye-bye.